Welcome to The Explainer. So today we're diving into the sort of invisible mechanical magic that keeps massive commercial buildings, power plants, and industrial facilities perfectly cool. You know that feeling, right? Stepping out of the sweltering heat into a crisp, heavily air-conditioned skyscraper or shopping mall? Have you ever wondered what exactly is doing the heavy lifting to make that possible? Well, we aren't talking about a simple window AC unit. No way. We're talking about massive, highly engineered pieces of equipment, some literally the size of school buses, known as vapor compression chillers. In this explainer, we're going to discover exactly how this incredible machine manipulates thermodynamics to actually remove heat. And, just as importantly, we'll look at the rigorous maintenance required to keep the whole shebang running smoothly. All right, here's the roadmap for today's explainer. First, the anatomy of the chiller. Second, the refrigeration cycle. Third, the heat transfer process. Fourth, the preventative maintenance schedule. And finally, key metrics and troubleshooting. Section 1. Anatomy of the chiller. Okay, so before we can even think about operating or maintaining this massive machine, it really helps to understand its vital organs. Just like the human body relies on different organs working together to survive, a chiller relies on specific, interconnected mechanical components to manipulate pressure and temperature. It's essentially a closed loop made up of four main parts. First, the compressor takes in low-pressure refrigerant vapor. Next, the condenser receives that high-pressure vapor. Then, the expansion valve suddenly reduces the pressure. And finally, the evaporator is where the actual cooling takes place before the whole cycle just repeats itself. It's absolutely fascinating to look closely at the compressor because it truly acts as the heart of the chiller. Just as your heart pumps blood, the compressor forcefully pumps and squeezes low-pressure refrigerant coming from the evaporator. By doing this, it drastically increases both the pressure and the temperature, creating this superheated vapor that has the momentum to travel through the rest of the system. Honestly, if this mechanical heart stops beating, the entire cooling process just flatlines. Section 2. The refrigeration cycle. Now that we know the organs, let's trace the exact step-by-step journey of the refrigerant as it flows through. This cycle happens in 4 dynamic steps. Step 1 is evaporation. Here, the refrigerant acts almost like a heat thief. It absorbs heat from the warm return water in the evaporator, boiling and changing from a liquid into a vapor. Step 2 is compression, where our heart squeezes that vapor, making it high pressure and superheated. Then comes step 3, condensation. That hot refrigerant enters the condenser, dumps its heat into a separate cooling water or air system, and condenses back into a high-pressure liquid. Finally, step 4 is expansion. The liquid is forced through the expansion valve, causing its pressure and temperature to drop rapidly. It emerges as a cold, low-pressure liquid, perfectly primed to steal heat all over again. To put that evaporation step into perspective, the physical result is actually pretty striking. The warm return water from your building enters the evaporator at about 12 degrees Celsius. As the refrigerant absorbs its heat, the water temperature drops significantly, leaving the evaporator at a crisp 7 degrees Celsius. And that 7-degree chilled water, that is exactly what gets pumped throughout the building to keep everyone comfortable. Section 3. The heat transfer process. So if we zoom out from the microscopic level of the refrigerant, we can see how heat is systematically expelled from the entire building. It's essentially handed off like a baton in a relay race. Heat generated by people, computers, machinery inside the building, all of that is transferred to the chilled water. The chilled water carries it to the evaporator, where it passes the heat baton to the refrigerant. The refrigerant then carries it over to the condenser, where it hands it off to a separate cooling water or air system. And finally, that cooling system rejects the heat entirely, literally throwing it out into the outside atmosphere. It's a beautifully choreographed, continuous flow of thermal energy leaving your building. You might be wondering, why do we use this specific, complex technology? Well, because for large HVAC systems, vapor compression chillers offer some incredible advantages. They provide highly efficient cooling, reliable operation, and extremely precise temperature control. And maybe most importantly, when we're dealing with massive capacities, like cooling an entire airport or an industrial plant, they offer much lower operating costs compared to other cooling methods. Section 4. Preventative maintenance schedule. All right, knowing how the machine operates is really only half the battle. Preventing the villains of high energy consumption and unexpected downtime is the other half. But before anyone even touches a wrench, safety first. This is absolutely non-negotiable.
You must follow strict lockout/tagout, or LOTO, procedures to ensure the equipment cannot accidentally start. You have to wear proper PPE, helmets, gloves, safety shoes, and goggles. Electrical isolation is a must before maintenance, and because we're dealing with specialized chemicals, you have to handle refrigerants according to strict environmental and safety regulations. It's really fascinating to see how these checks build into a rhythmic progression of care over the course of a year. On a daily basis, technicians check operating parameters like temperatures and pressures and just listen for unusual noises. Weekly, they inspect compressor mounting bolts, check motor currents, and verify water pump operations. The monthly maintenance gets a bit deeper, inspecting condenser and evaporator approach temperatures and checking the refrigerant charge. Quarterly, it's time to analyze the compressor's oil condition and test high and low pressure safety switches. And finally, annually, the system gets a full overhaul, mechanically cleaning the condenser and evaporator tubes, checking bearings, and calibrating all sensors. It's dense, for sure, but this consistent care is what prevents catastrophic mechanical failures. Section 5. Key metrics and troubleshooting. Think of this phase as the doctor's checkup for the chiller, where we take a close look at the vital signs. These key performance indicators are your ultimate scorecard. We want our chilled water supply temperature leaving the machine to sit between 6 and 7 degrees Celsius. We expect the return temperature coming back from the building to be between 11 and 12 degrees. We also watch approach temperatures very closely, which is simply the temperature gap between the refrigerant and the water. For the condenser, it should be 3 degrees Celsius or less, and for the evaporator, 2 degrees or less. Hit these exact numbers and you know your chiller is perfectly healthy. But what happens when things go wrong? Let's connect some common symptoms directly to their root causes. Say you have high condenser pressure. Well, that's often caused by dirty tubes or poor water flow. The solution is simple: clean the tubes. Experiencing low cooling capacity? You might just be low on refrigerant and need a recharge. If you notice a sudden spike in high energy consumption, your heat exchangers are likely fouled up and need a deep cleaning. And if the machine suffers from frequent trips, like it's constantly shutting itself down, it's highly likely there is a sensor fault or pressure issue, meaning you need to get in there and inspect the controls and protection devices immediately. So it is truly a marvel of modern engineering, isn't it? Next time you step out of the blazing heat and into a perfectly cooled skyscraper, just take a moment, look around, and ask yourself, is the mechanical heart hidden deep in the basement or high on the roof, beating at peak efficiency? Understanding this precise vapor compression cycle, the relay race handoff of heat, and the meticulous daily to annual maintenance required really gives us a profound appreciation for the invisible world of thermodynamics operating all around us. Thank you so much for joining me for this explainer. Keep learning, and I'll catch you on the next one.